So this is joint work with Vijayan, Rama, Mahesh, Marcos, and Hussam. So Ralph Waldo Emerson famously said, "A foolish consistency is the hobgoblin of little minds, to which I add, and of large clouds." If you look at today's cloud storage providers, they invariably replicate data for high availability, performance, scalability. Increasingly, they replicate data across data centers, known as geo-replication. This allows the data to survive complete data center outages, and it also allows that data to be placed close to clients, to customers that are worldwide, as we saw in the previous talk. In the face of such widespread replication, one of the key design decisions facing these cloud providers is what consistency do they provide to their customers? There's no correct answer. Oops. So if you look at today's cloud storage providers, they actually, and many of them, actually provide a choice of two types of consistency, strong consistency and eventual consistency. Again, as we saw in the previous talks, these are out there in the world. This allows the application developers to choose a space in this complex space of trade-offs between consistency, availability, and performance. Applications can choose a point in that space that meets their application needs. But there's a fundamental problem with this. And the fundamental problem is that the application developers have to choose their consistency at the time that they're developing their programs. And they don't have sufficient information to make informed decisions. Cloud storage providers do not give you performance numbers, so you don't know what the implications of a particular consistency choice is. And even if they did, the choice made now while developing your program may be the wrong choice 6 months from now when you deploy your application, or 2 years from now after it's been on the market for a couple of years. Okay? Furthermore, there may not be a single correct choice for all customers in all situations. So to illustrate this, we went out and we measured the performance, the round-trip measurements of the performance of doing a strong consistency read versus an eventual consistency read in the following situation. What we did is we put a primary copy of the data in a data center in England. We put a secondary copy in a data center on the west coast of the United States, a secondary copy in India, and we ran clients running the YCSB benchmark in all of those 3 data centers, and we also put a client running that benchmark in a data center in China where there was no local data whatsoever. And we measured the cost of the round-trip cost of Git operations running this benchmark. And what you see is that for some cases, the difference between an eventual consistency read and a strong consistency read could be 2 orders of magnitude. So now if I gave you this data in this table, and you were responsible for developing, let's say, a shopping cart application, what consistency would you choose? Well, we know from the Dynamo paper that was published at SOSP in 2007 that the shopping cart application wants to retrieve the shopping cart in under 300 milliseconds. Okay? So which would you choose? So if your customers were all in the US or they were in England, then clearly your best choice is to choose strong consistency. That provides the best customer experience. They're not going to see incorrect shopping carts, and they're going to get decent performance. But if you also have clients that are in India and China, now you're forced to choose eventual consistency. So if you're the application developer, that means you either write your program so that you provide eventual consistency for everybody, which is what Amazon did, or you have to write complex code in your code to try to figure out what class of user is running your application right now and what sort of consistency can I give them and take different paths in my program. That complicates your program. So this is the problem that motivated us to design the Pileus system. So Pileus starts as a conventional replicated key value store that replicates and shards data across servers in different data centers. To that, we add different choices of consistency, not just strong and eventual consistency, but also intermediate consistency choices. And then most importantly, we take these consistency choices, we integrate them into the service level agreements that are the contracts between the service level providers and the applications. This allows the service level providers to adapt their behavior to better meet the needs of those applications. So before I go into more detail on how we do this, you may be wondering, why the name Pileus? Turns out Pileus is a meteorological term for something known as a cap cloud. A cap cloud is a type of cloud that sits above other clouds. It rapidly adapts to the form and movement of those underlying clouds, and it's rumored to alleviate concerns about the CAP theorem. Okay, so our Pileus system model is as follows. We have a primary core of replicas, of storage nodes that constitute the primary core that use synchronous replication to remain strongly consistent. Outside that primary core, we have a set of other storage nodes that are known as secondary storage nodes. These nodes are lazily updated, so they lazily receive updates from the primary. There could be any number of these. They can be arbitrarily out of date, so they provide stale data. And they use lazy replication, as I said. All put operations in our system go to the primary core where they're done, and they're serialized and executed. Get operations can go to any storage node as long as that storage node is sufficiently up to date to meet the consistency, the desired consistency. From a given client may send its GET request to different storage nodes over time, either because those storage nodes go up and down due to failures, because those storage nodes have different freshness due to when they receive updates, because those storage nodes differ in the communication latency between the client and the nodes, and so on. So this system model mimics the architecture of many large cloud systems that exist today, including Windows Azure. But all of this detail is hidden from application developers by an API and a client library. So in this API, application developers perform GET and PUT operations using this API. These GET and PUT operations are nested inside transactions, which are nested inside sessions. For the point of view of this talk and for the paper, I ignore transactions, and I'm going to focus on the design, implementation, and evaluation of one operation, namely a GET operation that takes a key that it uses to fetch. It fetches data for a single key and bases that operation on a caller-provided consistency-based SLA. Okay, so what sort of consistency choices do we allow you to put in these SLAs? In addition to strong and eventual consistency, we support 4 intermediate consistency choices. We support causal consistency, bounded staleness, read-my-rights guarantees, and monotonic reads. All of these are described precisely in our paper. Their usage has been motivated in other systems and in other papers you can go read. So I'm not going to go through the details of them right here. We did not invent these consistencies. Our contribution is taking these consistency choices, adapting them to our system model, incorporating them into consistency-based SLAs, and evaluating them in the context of a geo-replicated cloud service. Okay, so what are the performance implications of choosing one of these consistencies? In this table, I expanded on the previous table that I showed you. So for each of the 6 consistencies and each of 4 clients running the YCSB benchmark, I show you the average round-trip time for GET operations in milliseconds. Again, we have the same configuration that I talked about before. We have a primary in England, we have secondary in the US, a secondary in India, and a client in China where there's no local replica. What you will see is that intermediate consistencies really do provide intermediate performance. The other observation from this table is that if you pick a particular consistency, the performance for that consistency really varies across clients. This is exactly the problem that we're trying to solve. Adding more consistency choices in Pileus, in fact, compounds the problem for the application developer because it offers him a broader choice of performance latency trade-offs, but it makes those choices more difficult. And that's why we invented consistency-based SLAs. So what's in a consistency-based SLA? What it does is it allows the application developer to specify in a declarative way the type of consistency that's tolerable for his application and the range of performance in terms of latency that's tolerable for his application. And so let me explain the structure of a consistency-based SLA by way of an example. This example is the shopping cart that I introduced earlier. So for a shopping cart, as we know from the Dynamo paper, the application developer would like to be able to say, I would prefer strong consistency as long as you give me a read latency of less than 300 milliseconds. Okay, so that's my top choice. That's the service I want from the storage provider. But what happens if the storage provider cannot provide that level of service? Should the storage provider provide weaker consistency? Should it provide higher latency? Or should it do both? It depends on the semantics of the application. In this particular application, the developer would like to be able to say, keep the latency bounded by 300 milliseconds, but it's okay if you give me read-my-writes consistency. That would be my second choice if you can't give me strong consistency. And he may go a step further and say, at the very least, I will tolerate eventual consistency as long as my latency bound is 300 milliseconds or less. Okay? So in general, a consistency-based SLA is a ordered sequence of pairs of consistency paired with a latency that's provided by the application developer based on the application semantics. And there could be any arbitrary number of these. We also allow the application developer to tell us the relative benefits or the relative value of each of these choices. And we do that by associating with each of, first of all, I should say that each of these pairs is what we call a sub-SLA. Okay? So associated with each sub-SLA, the application developer can provide a utility, a numerical value. The value itself is not all that relevant. What matters is the relative values of these different sub-SLAs. So in this particular example, the application developer has said that the top choice SLA is twice as valuable to me as the second choice SLA and 10 times as valuable as the last choice, meaning strong consistency is 10 times more valuable to me in this particular application than eventual consistency. So each get operation in our system takes one of these consistency-based SLAs as a parameter, as I said earlier, and it's up to the service provider to try to maximize the utility for every get operation maximize the utility delivered to the application. So how does it do this? First of all, the client, it's done in the client code, client library. The client library has to maintain some information about what's happening in the system. First of all, it has to know for each tablet or shard of data, what are the nodes that store that data? What are the nodes responsible for that key space? And whether those nodes are primary or secondary nodes. Second of all, it has to know how expensive it is to communicate with those nodes. What's the latency to them? It obtains this latency information itself. Each client individually measures the round-trip times that for the put and the get operations that it does to different nodes, and it records those in this table. If it doesn't regularly access some node, then it will periodically send a ping to that node, measure the round-trip time, record it, keeps the sliding samples of measured round-trip time so that if the network characteristics change over time, then it will adapt accordingly. And the third thing it has to know is it has to know how fresh are each of these nodes, how up-to-date are they. In our system, you may recall, all of our updates go to the primary core. The primary core serializes those updates, assigns a timestamp to each put operation. That timestamp is taken from a logical clock. And so each node maintains a high timestamp recording the latest put that it's aware of. So for the primary nodes, the latest put, its high timestamp is the timestamp of the last completed put operation. For secondary nodes that lag behind the primary, their high timestamps would be less than the high timestamp of the primary, but it still indicates the prefix of updates that they have received so far, and we assume that secondary nodes receive updates in timestamp order. So a single high timestamp is enough to completely characterize the set of puts that they have seen. Okay, so given this information now, how do clients perform get operations? Oh, I should say that as I already said, the first information comes from the configuration service and the rest of the information comes from the puts and gets that you normally put. Oh, I did say that the high timestamp, the other key point that I didn't say was that each node, when you do a put or a get operation, returns its high timestamp to the client in response to that operation. So the client takes that high timestamp received from the node, records it locally, so it has a local record of how up to date each of the nodes are. Its local information, of course, may be stale, but high timestamps are monotonically increasing, so at least it provides a lower bound on the freshness of each node. And that's sufficient for our purposes. Okay, so how do we enforce SLAs via node selection? For each get operation that takes a key in an SLA, we go through all of the sub-SLAs in that SLA and all of the nodes that store that key, and we compute the probability of this particular node being able to meet the latency bound specified in that sub-SLA. This is a straightforward computation given the round-trip samples that the clients have recorded, right? Second thing we do is, for each node in each SLA, we compute the probability of that node being able to meet the consistency required by that sub-SLA. The details are in the paper. Again, we can base this purely on local information at the client, on the high timestamps that he's recorded and other information he knows about gets and puts that he's done in the case of session guarantees that he needs to provide. Given these two probability computations, the client can compute the expected utility of performing this get at that particular node. He simply takes the probability of meeting the latency bound, multiplies it by the probability of meeting the consistency bound, multiplies it by the utility of that sub-SLA. That gives him an expected utility. Given the expected utility for all of the nodes, he can then choose the node with the highest expected utility. There may be a tie. There may be multiple nodes that have the same expected utility, in which case we choose the closest one. Other tie-breaking procedures are reasonable. For instance, you might go and choose the one that can provide the freshest data. Once it chooses a node, it sends the get operation to that node. It's performed at that node. It measures the round trip time, how long it takes. It records that in its local table. It updates its record with a high timestamp that that node tells it. It takes that data and returns the data to the caller. And it also, importantly, returns an indication of how consistent that data was. Okay, so note that the consistency returned to the caller may in fact be different than the consistency that the client thought he was going to get when he chose this node. He may have chosen a node thinking it was the only node that could provide, it could only provide eventual consistency and that was good enough for this particular SLA. But in fact, when he got the data back, he could verify that that data provided a higher guarantee like read-my-rights guarantee, in which case he will tell the client that he got read-my-rights data. Okay, so how well does this work in practice? We did a bunch of experiments. They're reported in the paper. I'll tell you a couple of them. First, our system configuration that we use for all of these experiments is the one that I've talked about before. A primary in a data center primary data in a data center in England, secondary data centers in the US and in India, and we have clients running in those same 3 data centers as well as a client running in China. We use the YCSB benchmark, and we compare Pileus to 3 alternative simpler schemes for node selection. We compare it to a scheme that always sends gets to the primary. We compare it to a scheme that randomly chooses nodes, so that means 1/3 of the gets go to the US, 1/3 to England, 1/3 to India, and we compare it to a scheme that always chooses the closest data center. So if you happen to be running in the same data center as the data, you will choose your local data center. In the case of China, where there's no local data, it goes to the US because the US is the closest data center. And then the comparison metric that we use is the delivered utility, the average delivered utility per get operation. Okay, so the first experiment, we used the SLA, the shopping cart SLA that I talked about earlier, though it's in slightly simplified form. I removed the first sub-SLA, and so in fact it only has 2 sub-SLAs, one that says I want read-my-rights guarantees, and the second one that says I'm willing to accept eventual consistency. For this SLA, here's the results we get for the 4 clients across the right, across the bottom, and for the 4 different types of node selection schemes from primary, random, closest, and Pileus. First thing you notice is primary selection works really well if you're close to the primary and it provides at no value whatsoever if you're distant. Random selection rarely works well at all. Okay, so what about Pileus? So in Pileus' case, when we're in the same data center as the primary, then of course we always send our request to the local data center. We get perfect utility. We get the maximum utility possible. That's a no-brainer. If the primary is in the US, then the client 91% of the time sends the request locally to the US. These are the cases where it knows that the US is up to date enough to guarantee the read-my-rights guarantee. In 9% of the cases, it thinks the US is too stale. It sends the request to the primary in England. In both cases, it meets the top-level SLA because England is close enough to meet the latency guarantee, and they both meet the read-my-rights guarantee, so it gets maximum utility. It meets the top sub-SLA 100% of the time. If we simply sent all of the requests to the primary in England, we would also meet the top SLA 100% of the time, but there's a fundamental difference, and the fundamental difference comes with the average latency. So if you looked at the average performance of these get operations, because Pileus is smart enough to know when it can send data locally. We get an average round-trip time of 14.5 milliseconds compared to the scheme of always sending to the primary, which gets a round-trip time of 148 milliseconds. So we save an order of magnitude of performance without giving up any utility to the application. Okay, for the clients that are in China and India, they basically split their requests between the US and India, the client in China favoring the US, the client in India favoring India. They don't meet the top SLA 100% of the time, but they come close. They meet it 96% of the time. So in all of these cases, Pileus provides the maximum utility, or the most utility of any of the schemes. But you might say, well, wait a minute, what about this closest scheme? It looks like it's pretty similar to Pileus. What's going on there? Well, in the case of the closest scheme and Pileus, when they're both in the primary data center, of course they do the same. For the clients running in India and China, Pileus is just marginally better. It's not really very significant. For the one in the US, you might think that the bars look pretty close, but these bar graphs are deceptive. So if you zero in on this, you'll find out that the closest scheme fails to meet the top sub-SLA 9% of the time. So if this was a shopping cart application, that means 1 out of 10 times almost when you go to check out, your shopping cart would have missing items in it. That would be totally unacceptable. It would lead to unhappy customers and unhappy sellers, whereas Pileus guaranteed that 100% of the time your shopping cart was accurate. Okay. I should say the reason these differences are not more substantial is because this particular SLA places no value on strong consistency, right? And so if you care only about one of these relaxed consistency models, then most of the time, pretty much any node is sufficiently up to date to meet the consistency. That's not completely true, but it's true in a lot of cases. So let's look quickly at one more SLA that's slightly different, that does put more value on strong consistency. This is an SLA. It's interesting because it varies the consistency and it also varies the latency. It says, if you can give me strong consistency or eventual consistency, if you can give me a quick answer. If you can't get me the data quickly, then I'm willing to wait, and if I have to wait, I want a strongly consistent answer. Okay, it doesn't make any sense to wait for a weaker consistency answer. This SLA is motivated by an application we describe in the paper for password checking, but it's also, we just talk about other applications that would use a similar SLA. For this SLA, these are the results we get. You see that, in fact, because it favors strong consistency, the clients that are farther away from the primary suffer more. They don't, in fact, get very high utilities. But again, Pileus provides the most utility of any of the schemes. And for any of the schemes, there exists at least one client for which Pileus provides double the utility. So those are the results I'm going to show you. So in conclusion, there are 3 points I want you to take away from this talk. One, it's practical to build a system that provides intermediary consistency guarantees, not just strong and eventual, and in doing so gives you a broader space of performance for read operations. Two, by incorporating consistency into the service level agreements, we allow application developers to specify their tolerable consistency and latency without being locked into a particular choice and without having to complicate their programs. And three, based on consistency-based SLAs, the cloud storage providers can deliver high utility to their customers in a variety of situations where the clients are different, the network is changing, the replicas are changing, and so on. So thank you. I'd be happy to take questions.
Okay. Oh, very nice work. I noticed that in your latency metrics, it seems that you use the kind of hard deadline, not soft deadline. So could you say something about the tail distribution of the delays in your experiment?
Oh, so yeah, I didn't show you. So in fact, in our experiment, the variance in the network delays was not all that high. So we took that into account in the measurements, of course, but in practice, the variance was not very high throughout these experiments.
So all you use is the average delay, or?
Pardon me?
What I'm concerned is about the delay, the tail distribution of the delay.
So if there is a large tail distribution, then our system will adapt to that, and it will sometimes fail to meet the SLAs, right? So you make it a situation where you think you can get to a server within a time bound, and you miss that SLA for that reason. We did not actually see that in our results because the delays variance was not very high.
Okay, thanks a lot.
Let's take a question from the great question poser in the sky. How do developers choose utility values? In particular, it seems like evaluating the application level impact of different guarantees would be challenging.
Absolutely, it is challenging. So in theory, you would choose your utility based on the actual cost of a weakened consistency. So for instance, if you had a shopping cart application and you knew that eventual consistency led you to have inaccurate shopping carts, some percent of the time, and that in turn led to unsatisfied customers who left the system, and then you could compute the cost for that, then you could use that to derive your utilities. In practice, we did some experiments in the paper and showed that the choice of the utility values, the results were not all that very sensitive to them. So I think in practice, simply ordering your choices would do, pretty well.
I'm Jonas Wagner from EPFL and have a similar question. It's not about choosing utility, but about how would I, as a developer, reason about what I get? Do I have to program my application and distinguish 6 different cases for 6 different consistency levels that I might get?
So you definitely have to write your application so that it's correct in the face of any of the consistency levels that you say are acceptable in your SLA, right? It doesn't have to be all 6. If you can tolerate all 6, then you would write your application to tolerate eventual consistency, and that same application would then presumably run for the higher level of consistencies, right? So the idea here, the target applications are those that can tolerate a relaxed consistency but benefit from increased consistency.
Thank you.
I mean, if you want to write case statements in your code to deal with different types of consistency data that you get back, you could do that because we tell you what consistency you are. But my experience is that typically these inconsistencies just get reflected back to a user or something, and there's no specific application code that gets written.
Okay, thank you.
Robert Veronesi, Cornell. So I assume by strong consistency you mean linearizable with respect to a sequential specification of a shopping cart. And is it the case then that if once you have one client getting back a result that says, it's like read my last rights or something like that, or a weaker consistency, you can never tell another client after that that the execution was linearizable. So you can only adapt down, in other words. You can never go back up to strongly consistent execution.
No, that's not true at all, because of our update model, because all of the puts go to the primaries are always strongly consistent, so you always have a point of reference from which you can get strong consistency independent of what the other read clients do.
Dave Anderson, Carnegie Mellon. So Doug, if you go back to slide 8, you have some numbers that I'm trying to understand. You show an abysmal number for the latency of causal, and yet the reason that you think about causal is that it is the strongest form of consistency that can still satisfy all of its reads entirely in the local replica. And so I'm having a hard time understanding how one can make causal be more substantially worse than read my own rights, which can also execute locally.
Right, so first of all, what you said about causal consistency is only true if all you're providing is causal consistency. If you're providing only causal consistency, then you can do local rights. But if you want to do strong consistency, then you need some reference point for which to do strong consistency. And so you basically, that causes our causal consistency to be more expensive because it can't do local rights or local reads all the time.
So causal
Understood?
in your system is actually, in a sense, fundamentally more expensive than causal in a causal-only system.
In a causal-only consistency system, it's fundamentally more expensive, correct?
Interesting. Thank you.
Yes.
This is good. Dave asked one of my 2 questions. I'll ask a different one. It's a variant on Robert's question, actually. Once, in a given session, you showed us sessions and then you said you weren't going to talk about them.
Correct.
But once you've returned a weaker form of consistency than someone wanted, should you then drop the consistency for everything else since there's no point now? Bets are off in some sense.
Not necessarily. So the sessions guarantee still makes sense. So you could within a session say, I do a get that does strong consistency and I do another get for a different key that does eventual consistency, and they're unaffected by each other, right?
Well, I guess, yeah, if you're the expert.
Yes.
Okay.
All right, let's take another question from the web. The statement intermediate consistency, intermediate latency, how is that tied to the replication topology that you use? And what about in a multi-master context?
Okay. So, so for this talk and for our system as I presented in the paper, we assume we have no control over the replica configuration. So given a certain configuration of replicas, we try to do the best to meet the SLA given that configuration. Okay, so it doesn't really impact how the replica, unlike the previous talk where they were actually trying to dynamically change the replication policies, we assume that someone has come in, configured the replicated system, and in practice that's usually happens because moving the data dynamically is too expensive if you have large data sets. So we're assuming that we have no control over where the replicas are located. That's a given for us. And the question about multi-master is we don't do multi-master, we do primary core update.
Pedro Españates, Intel. I was wondering, given the way you've structured your SLAs, they are this monotonic sequence of rules with respect to the utility, but not necessarily with respect to latency or consistency level, right, for that matter. That makes it attractive to be wasteful. So in some sense, I can read my writes, but not strong consistency, but still go and extract as much latency out of the system as possible, which the client, the user, the developer, was willing to sacrifice. So could you imagine a way in which you could switch how you evaluate policies to adhere to the deadline with respect to consistency levels that you can give and not waste resources that were not needed anyway?
You could imagine that. That's the short answer to your question.
If you're paying for it.
Right. So in practice, what I expect to happen is that these service providers are going to charge you different amounts of money for different levels of service, right? And once they do that, as long as those charging policies are consistent with the order in which you value those services yourself, then you're okay. If there are inversions in that order, then you're right. You could have opportunities for clients to choose things that are sort of, wasteful.
I was talking about the system.
Correct.
But I'll let someone else ask a question.
Last question. So I guess the latency numbers in the states table are average numbers, and there must be some.
These are average numbers, absolutely.
Right. I'm not sure about the degree of uncertainty, but my point is, it almost seems like the programmer can give multiple choices at the same time. If I'm lucky, I get strong consistency with small latency. It seems like I can, for example, issue 2 requests, and I get a fast, inconsistent result first, and wait until I'm satisfied with the consistency.
You could do that.
So can you comment on how, what's the standard deviation? Do you always get this kind of latency, or?
Oh, so the standard deviations are actually very high, right? Because we don't, so in this situation, we only have 3 replicas, right?
Yeah.
And so if you look at the US numbers, there are 2 choices. You go locally, in which case you get 1 millisecond response time, or you go remotely, in which case you get 148 millisecond response time. And so it's a bimodal distribution, and so the standard deviations in these averages is quite high.
Okay. All right, thank you.
Okay, thank you.